Well, welcome back. We got worksheet 3, number 3. I'm going to walk you through it with my interior monologue full blown here. So, determine the final velocity of the cart after traversing across this frictionless surface. Use the ground as the zero level. We define my system first. Looks like I got this cart here. It goes down. It's going real fast. It wasn't going fast at the beginning there. It was up high. And then it goes low, and it's got some mass there too. Great. Well, we're probably going to want to analyze the energy of that cart. And I see that it goes through a height change here. So I'm going, gravitational potential energy would be an easy way to describe this. And if I want to use gravitational potential energy, I got to put the Earth in my system, the two things that are pulling each other. The Earth pulls the cart pulls the Earth. Okay, and that anytime you have some potential energy, you got to have those two things that make that potential energy in your system. All right, so now how fast is it going at the beginning? 0, so it's got 0 kinetic energy at the beginning. It's up high here, so it's got some gravitational potential energy, that's for sure. And then at the end there, it goes real low, and I might even say that this point right here is my gravitational potential energy of 0 line there. So that means that this would be 0 over here. And it's going real fast. Why is it going fast? Well, gravity pulled this thing down. It lost the gravitational potential energy and gained the kinetic energy. Or maybe a better way to say that is the gravitational potential energy turned into kinetic energy. And so energy can't be created or destroyed. It's going across this frictionless surface here. And so we're kind of assuming that maybe no thermal energy is increasing. Now you could do this as thermal energy increasing, and maybe I'll change my answer at the end and to do it with thermal energy. We know that the friction between the wheel and the ground, what type of friction is between that wheel and the ground? That's right, that's actually static friction between any wheel and the ground, assuming it's rolling normally, not skidding across the ground there. And if it's static friction, how much heat does static friction generate? Absolutely 0. So static friction isn't causing this wheel to slow down nor heat up, but instead it's actually the deformation of that wheel there. So while this is written to kind of guide you along to say that there's no thermal energy from the frictionless surface, we actually know a little bit better, and we go, oh, you would have to say like no deformable wheels or no deformable surface that it's rolling on there to be particular. But either way you do it, it'll be just fine. So let's go and let's calculate this now. Well, what am I saying here? Just like in the last problem, I'm saying that, hey, the gravitational potential energy at the beginning is equal to the amount of kinetic energy that we have at the end. We go look up the formulas for this guy, and that's the mass times the gravitational field strength times that height at the beginning there. I guess I could put that as HO for the height at the beginning there particularly. And the kinetic energy is just 1/2 mv squared. Now I go and I solve for, what are we solving for? To the final velocity there, so V is a big question mark there. And so same tricks that we employed last time, we're just doing algebra here. So I look at the mass and I go divide both sides by mass, mass cancels out here, and now I'm just going to go and solve for V. Hey, that's the exact same as the last problem there, so I'm going to multiply 2 on both sides there to get that 2 out, and I'm going to take the square root to get rid of that square there. And so let me change back to purple. And that's going to be V is equal to the square root, oh, that's a different purple, G2GH, and the height at the beginning specifically. And let me just go and plug in some numbers there. What do we know? We know, let me get back to a different color. We know that G is 9.8 as it always is on Earth there. The height there is 5, and so I go and put these guys in for there, and we get, wait, it's the same velocity as the last problem there because it's the exact same numbers. So is that 9.988, I think? Let's see, I still have it in my calculator. 9.899, sorry. 9.899, oh, and I used the different purple, sorry about that. And we get the exact same velocity. Oh, so that means that, going back to number 2 there, that it doesn't matter if it's rolling down the ramp here, where it's not actually like heating up at all, or if it just falls straight down, it'll be going the exact same speed at the end regardless. Now, if we went and did this so that thermal energy was there, now it would be a little bit different. Okay, so that's that. Let me erase some of that, and let's go do this again with thermal energy and see what happens. So what's going to change? Well, this is going to change a little bit. We might say that, hey, thermal energy, maybe it increases its thermal energy a bit because it's heating up, it's rolling on that ground there, and we got real, maybe rubber wheels that are like actually deforming like the tires in your bicycle or your car. And so some of that is causing it to slow down, aka some kinetic energy is now being transferred into thermal energy. So what is this saying? Well, we look at this conception and we go, hey, the gravitational potential energy at the beginning is equal to the kinetic energy at the end plus my thermal energy at the end. Now, if I go and plug in all of my equations like we did before, this is mg h naught, and this will be 1/2 mv squared plus, wait, do we have an equation for this? And no, we have no equation for this. Why not? Well, thermal energy is actually incredibly complex to be able to calculate it directly. That's something that if you went into graduate level physics, maybe you'd start doing some of those calculations or graduate level chemistry. We're nowhere near that, and we don't want to get into that. So generally, you might have some conversion factor that might be given to you to be able to calculate this kind of indirectly. What do I mean by that? Well, I could rewrite this problem. So instead of saying something like that it's going across this frictionless surface, I might say it's going across this surface and 10% of the original, that's a terrible the, of the original energy is converted into or lost to thermal energy. So you would have to be given some sort of statement like that that's telling you it's usually just a percentage of the energy that's actually being converted into that. Now let's go ahead and let's do this as if it was 10%, because why not? Well, if it was 10% of the original energy, and the original energy is just this 5 made-up bars of gravitational potential energy, well, that amount of energy is going to be this guy right here. So that means that in this case, I know whatever number this is, 10% of that is this thing over here. Well, how could I write that? Well, 10% is just 0.1, right? And so now I'm going to multiply that by whatever number that is. Well, I don't know what the number that is yet. I could go calculate it if I wanted to, but I'm just going to write it with variables here because why not? It's, let me write it in parentheses there instead of the multiplication dot. So I have 10% of whatever this number is, and that's just mg h naught. Now, notice when I do this, I can actually find some little mathematical shortcuts, you might say, to be able to solve this. Hey, this guy over here, this is like almost the exact same expression or term as this thing right here. And let me, to be clear, let me put a 1 in front of that because that doesn't change it. Multiplying that by 1, it is a 1. We just don't write it all the time. So now I go, hey, I got a 1 of those guys there, and I have a 0.1 of these guys over here. Could I move this over to the other side? If I wanted to move this green term over to the other side, how would I do that? That's right, you're just subtracting because I'm adding there, and the inverse operation of adding is subtraction, or the inverse operation of addition is subtraction, is the best way to say that. So I subtract that over, and 1 minus 0.1, because it's the same term there, 1 minus 0.1 gives us 0.9 mgh naught. Now that's equal to 1/2 mv squared. Now let's go make sure that this makes sense. This says that 0.9, that's 90%. 90% of that original energy is now kinetic energy. Well, is that what we were saying conceptually over here? Well, we did. We just didn't use the actual percentage because we didn't have that at the time. And we said, hey, yeah, some amount of the gravitational potential energy, most of it went into kinetic energy and some went into the thermal energy there. Now, if we had that 10% at the beginning here and we wanted to make this even more accurate, which you don't have to, but sometimes it's helpful just for your understanding to be able to do that more accurately. 10% of 5 is just 0.5, so I could go make that 0.5, and then I would make this guy 4.5. Now, you don't have to do it like that, but sometimes it's helpful just for you to think about it and think about it a little bit more accurately. And so now I go, okay, yeah, I'm doing the exact same thing here, and that's exactly what this phrase is saying. So now if we go and you solve for this, we see that the mass, all the same things happen. The mass cancels out here. Multiply by 2 and take the square root of that. And so multiply by 2, I get 1.8 there. So I have 1.8 g h naught, and the square root of that is equal to v. Now I go and plug that into my calculator there. And I get 9.39 meters per second. Now, I compare that to what we had previously. Without any thermal energy there, we said the velocity was 9.899 meters per second. And I go, okay, well, does this new one make sense? Well, yeah. If there's like, the tire's deforming, that's going to cause it to like slow down like it does when I have kind of a flat tire or more flat tire on my bike. And so it won't be going as fast. And yeah, we found it to be not going as fast. That also makes sense looking just at the LOL diagrams, because now, yeah, I don't have as much kinetic energy, and I know that that corresponds to how fast things are going. Cool. So we can do this both without any thermal energy being transferred there, kind of an ideal situation. That's how it was originally written. Or we can also add in if thermal energy is present and things are heating up and therefore slowing down because of that. And again, it would have to be written something like this with giving you some sort of like percentage transfer there. All right, have a beautiful day.